Okay, hi. So we are now in the last week of the syllabus, and there are some topics that are not really programming topics as such, but basically they are associated with C and C++. So if you tell someone that I've done a course in programming, that too with the help of the C language, people might actually expect you to know these things. So this is why we are just covering these things for the sake of completeness, I would say. So just some recap. We actually had seen these things in the introductory week zero, but I had also shared some resources with you guys for studying Boolean algebra. I'm hoping that by now you are far more familiar with this term. So basically, just to recap, in Boolean algebra you have variables whose value can only be either 0 or 1. Then there are three basic functions that we talked about. The AND function, which basically means if two or more Boolean variables are there, AND function produces a 1 if and only if all the values are 1. Similarly, the OR function, where we knew that an OR function will produce a 0 if and only if all the values are 0, otherwise it produces a 1. And the NOT function is basically it just inputs the opposite of the variable's value. So if the variable's value is 1, it produces 0, and vice versa. Similarly, in continuation, we had a look at the logical operators in C. So these logical operators performed these Boolean functions, okay, over expressions. And for example, the logical AND operator performs ANDing of two C expressions. So for example, if E1 and E2 are two expressions, E1 ampersand ampersand E2 is 1 if and only if both expressions are 1, and otherwise it is 0. It can be it can be more than 2 as well, but basically it is evaluated always for 2 operands, so that is why we're just considering it for 2 operands. Similarly, the logical OR operator will perform ORing of 2C expressions. So if this E1 or E2 will be 0 if and only if both expressions are 0, otherwise it will be 1. And then this NOT operator, it used to apply on a single C expression, and it basically used to invert the value, right? So you remember that if the expression's value evaluates to 0, it will invert it to 1, or if it was 1, it will invert it to 0. So now there are some more operators in C which work similar to logical operators, but they are not really logical operators. Okay, so these logical operators, the final output of them is a 0 or a 1. There are something known as bitwise operators. They basically work over integer operand and produce another integer as output. Okay, so now this is where the things start getting different. Okay, so the logical operators, they will give you a 0 or a 1 at the end of the day. The output will be a 0 or a 1. Here it will be some generic integer, not necessarily 0 or 1, right? So these operators are applicable only to integer operands. That is the first thing that you have to understand. You cannot apply these bitwise operators to any other type of operand, just integers. And another thing that you should know is that it is not recommended to use them with negative numbers, as the output may be unpredictable. We'll have a look at some of the examples, but this is, it is highly recommended that you use them only with positive integers. So the bitwise operators, as the term suggests, actually works at individual bit level, right? Bitwise, right? So each bit, the result is calculated on a per bit basis, and the result for a particular bit is not affected by the results of any other bits. The three logical operators in that we have already seen, right? The AND, OR, and NOT operators. They have their bitwise um, bitwise what can I say, counterparts. We'll see how a bitwise AND is different from a bitwise from a logical and so on and so forth. But basically the basic function that they perform is still the same, right? ANDing and ORing and inversion. It's just that they do it in a different fashion. There's one more important Boolean function that we had not discussed, because I thought you'll study it when you study Boolean algebra in detail. That is the XOR function. Okay, the XOR function is also known as the exclusive OR function. By when basically the OR function that we usually use is also called as inclusive OR. Okay, so this is actually the exclusive OR, which outputs a 1 if either of the two inputs is 1 but not both. Okay, so this is the difference between XOR and OR. The inclusive OR will give you a 1 as long as either of the inputs is 1. The exclusive OR will give you 1 only if either of the two inputs is 1 but both of them are not 1. Okay, so this is the difference between exclusive OR and inclusive or normal OR that we call. So this is something that we have already seen, and we have discussed this many times before. But basically, whenever we are talking about data being represented in memory, we know that at the end of the day they have their binary representations which are stored in a bit by bit fashion. So assume that you have some integers, two positive integers. This is they are being represented here in 2 bytes or 16 bits. And uh, so this is another thing that we discussed, that the actual way in which these numbers are represented in the binary. For the positive numbers, it doesn't matter, right? It's basically the same way. You simply store their binary representation, and if required you just add more zeros towards the left of the number. But if you're trying to represent a negative number, then things become slightly difficult, because then you have to figure out whether it is sign magnitude form or one's complement form or two's complement form. Usually it is two's complement, but we cannot be sure. That is the idea. So the bitwise AND operator, it actually works like this. So the ampersand operator performs ANDing of ith bits of two integers in parallel. So ith bits as in this bit with this bit, this bit with this bit, this bit with this bit, so on and so forth, right? So just assume that there are 16 ANDing operations going on here right now, right? One each for each bit, the ith bit. And the only value of I here that you can see where both inputs are 1 is this bit number 13. That is why in the output you will have 1 only on the 13th bit position, and everything else becomes 0, right? This is what it says. This is the binary representation of 6. And by the way, all other things become 0 because either at least one of the two inputs is 0. That is why the output becomes 0. And you can interpret all these three, right? This as well as this, right, as some integer being represented in 16 bits, right? So this is, we all know, this is 6 and 13, 110 1101. If you have read Boolean algebra by now, these numbers would be in your memory already. You don't really have to look much. And then when you take an ANDing operation on these, this is what you get, and this is essentially the binary equivalent of 4. Similarly, if you do an ORing of uh, these two integers at a bitwise through a bitwise OR, the bits 12 to 15 actually are becoming 1. Why? Because either of the two bits is 1. Okay, wherever you can see that both bits are 0, the output is 0. But here, even if one of the bits is 1, the output is 1. And again, when you try to interpret this as as an integer, it becomes 15, 11114 bit. In the NOT operator, you only need you only have one operand. Okay, so again, this is the operand, and you can see that. So basically now you can see that all these leading zeros, they get flipped to 1. Okay, and this is one of the issues. Okay, because this flip, depending upon how you are actually storing the numbers, could also cause a major issue with certain representations. For example, in certain representations it could be sign magnitude form or even the basically any kind of form where you are going to store one of the bit, especially the leftmost bit, as a signed bit. There this not operator is not actually going to take care of the sign bit, so it's not going to treat the sign bit differently. So even the sign bit will be flipped. So basically what exactly does it get interpreted to depends on the actual representation of the number. So for example, if I assume that these 2 bytes are representing an unsigned integer, then this making making a knot of 6 is going to give you the output as 65,529. And if you actually start considering it as a 2's complement representation of a signed integer, that is an integer that has a sign as well, then actually this comes out to be -7. You don't have to worry much about why it comes as -7. For that you'll have to go into the detail of 2's complement representation, but the idea is the same set of bits can actually be interpreted in different fashions. As you know, whenever you have a 1 on the leftmost bit. So this is something that you have to be careful about whenever you use the not operator. It is possible to interpret it into two different ways, right? So the sign itself can actually flip from 0 to from positive to negative, or vice versa. The XOR operator, the it looks like the caret sign. It is the caret sign. Basically it actually depends on the number of ones that you have for inputs. Okay, so you can see that it will actually produce a 0 when all zeros are there, but as soon as it starts getting seeing ones, it actually counts how many ones is it seeing in the input. So for instance, on bit number 12, bit number 14 and bit number 15, it only sees one of the inputs as 1, so the output is 1. But on bit number 13 here, it's basically sees two ones, right? And here the output is also 0, and this is where this is where it is actually different from the inclusive OR, the OR that we usually associate as the ORing part, where as long as you have one input as 1, the OR gate or the OR function returns a 1. So this is how XOR is different from OR, and again you can interpret this as a different integer as well. So there are two more operators that are there in C. They are not really, even though they work at the bit level, they're not really Boolean operators. Okay, they are not really Boolean functions in some way. They are, the probably a best way to look at them is that they are actually arithmetic operators. Okay, both these operators, they apply to a single integer. So even though the operand, are there are two operands, basically the application is on a single integer only. What happens is these operators, they are known as shift operators. They actually take up the bit pattern, the 16 bits pattern that we have just seen. They take up these bit patterns and they shift them, okay, either left or right. And then when you shift them, some of the bits will actually go out, right? I mean, it's similar to how you pop out something from a stack, right? So similarly, when you shift a bit pattern to left or right, some bit will actually go out, that is lost from the memory, and then some space gets created on the other end, and on that end you pad it with zeros. This is the idea, right? So the left shift operator, it looks like this. You might have in C++ you might have seen this as a you use it with C out operator as well, the C out statement as well, but basically that is not the same thing. This is a shifting operator, and what it is doing is that it takes two operands. The first operand is basically the integer that I was talking about. The bit pattern of this integer operand is shifted to the left by the number of positions that are equal to the second operand. We'll have a look at what it means. Similarly, the This is for example, what does this mean? 6 left shift 2 means shift the bit pattern of 6 to the left by 2 positions. So you can understand that even though these are two different operands, the actual operation is just happening on this particular integer. The left shifting of any bit pattern is actually uh, equivalent to multiplication. We'll have a look at the example, but the idea is that whenever you shift something to the left, it is essentially a kind of multiplication. Similarly, the right shift operator, it looks like this. Okay, you can see, how they are similar. This is pointing to the left and this is pointing to the right. So it does exactly the same. It's just that um, the bit pattern is shifted to the right by the number as the second operand. So for instance, 6 right shift 2 means shift the bit pattern of 6 to the right by 2 positions. The right shift of a bit pattern is basically a kind of division. Okay, so this number, whatever number is here, it gets divided by some number. Okay, and what that number is, that we'll just have a look. So this is an idea that, now I have 6 as 6 being represented as this bit pattern. When I apply this left shift operator to it, um, essentially this particular bit, it goes out, it gets lost, and then all these bits are shifted by one position to the left, right? So you can see this 0 comes here, this one comes here, this one comes here, so on and so forth. And then there is a position that gets vacant, which gets filled up by a 0. Similarly, if you shift 6 by 2 positions to the left, then these two bits, whatever they were, they basically get lost, and everything gets shifted by 2. This 0 comes here, this one comes here, this one comes here, so on and so forth. um, Two positions are vacant where we fill up two, where which we pad up by two zeros. Now a left shift by k position of an integer means that it is getting multiplied by 2 to the power k. And you can see here, if you check the interpretation, if when I shifted it by 1, this becomes 12. When I shifted it by 2, this becomes 24. If I shift it by 3, it will become 48. 2 to the power 3 is 8, into 6 is 48. So you can see the number of positions you keep on shifting to the left. It is essential. It is essentially multiplying the number by 2 to the power k. This is what I was talking about. Since the leftmost bit will also be removed, so it will actually get overwritten by whatever is here. For instance, here in this case, and it will be overwritten by whatever was here in this case, here, sorry, by this case. So the idea is, because the leftmost bit is going to be lost, it is possible that there is a flip in the sign of the number if you are talking about numbers being stored as signed integers and not unsigned integers. Similarly, it is just, the exact opposite what happens with the right shift operator. You actually shift these bit patterns to the right, so this one comes here, this one comes here, this 0 comes here, so on and so forth. This particular bit gets lost, and then we add an additional 0 from the left side. Similarly, if I'm shifting it by 2, I add two zeros here, and then this one actually moves out. This one is now lost. Only this one is here, this 0 is here, so on and so forth. The right shifting of an integer by k position is essentially equivalent to its division by 2 to the power k. Now this division is the integer division that we know. Okay, the integer division thing that you guys have already seen. So that is what is happening here. If you divide 6 by 2, it becomes 3. If you divide 6 by 2 to the power 2, that is 6 by 4, the answer is 1, right? Because 6 by 4, the integer division 6 by 4 will give you 1. uh, Actually, this, I think, yeah, this has to be 0. I'll just I'll change it in the slides. This has to be 0. These two things are 0. Okay, since now here again, because the leftmost bit, as soon as you start shifting it right, the leftmost bit will actually become 0, right? I mean, because we are padding it that way. So what happens is this 2 has the potential of flipping your sign. If it could have been a negative number, actually it should be minus 2 plus. Okay, so it could have been a negative number before, but after shifting it, it will become positive number. So this is some of these are some of the things that you'll have to understand, that whenever you use these operators, you have to be a bit careful. So this example just shows everything that we have seen till now, all the operators and their outputs. So some finer points, the data types which you can use with these bitwise operators are char, short, int and long, the integer types. There are many operators which are left as undefined in the standards. Okay, I have given a link, I think, in the homework. Yeah, there is a link, so you can read that link. There are certain operations which are not defined at all in the standards, so even if you try them, um, there there's just no guarantee of what their output would be. Okay, they you might be able to reason about them in some way, but the standard doesn't guarantee any kind of consistency related to that. So this means that the output might actually differ from one platform to another. So that is actually an implementation detail. The bitwise operators can also produce in results which may not be easily understandable, right? So for example, the bitwise not operator can flip the sign of the integer operand that we saw as an example. And these shift operators, even though we know they mean multiplication and division, they can very easily produce results which are which basically involve overflow or underflow, right? Because some bit might actually go out of the range in which we were expecting the result to be, and then there could be an underflow or an overflow. So these bitwise operators are usually employed in cases where performance is of utmost requirement, right? So we want things to happen extremely fast. So usually you will watch it, you will see their use in lower level libraries, where people try to formulate the logic in terms of these bitwise operators so that they run faster. Okay, why exactly do they run faster? No, that you will study in your computer organization course. So there is some homework. I will make the changes in the slide. What There are two corrections, I think, but we will discuss this on Monday. Bye.